It's a huge honor to be here, and thank you so much for coming out tonight to hear this presentation. I do have an ESA logo at the top because this is my current role, and I'm very proud. This is really my dream job. But this is not a corporate talk for the European Space Agency. This is a very personal perspective through my career. And actually coming here tonight and my visit to Slovenia this week, it's made me reflect a little bit on how I've got to where I've got to. Sometimes when one is pursuing one's careers and dreams, you get busy and life rushes by. I mean, Andrea and I began to collaborate. We were saying tonight that the last time our children saw one another, my youngest son was 18 months old, and today he's 18 years old. So you can see those personal and professional ties. And so as Andrea said, you know, there are a number of titles there, but I particularly wanted to show you my site in Spain. So I head the European Space Astronomy Centre in Madrid, and I'm the most senior diplomatic representative of ESA to the Kingdom of Spain and Portugal. And we have a castle as well. So the view from my office is 3 radio antennas and a 15th century castle, which is outside of our boundary. But it's a very, very special place. It's also a site of special scientific interest in the countryside. But actually, more importantly, I began to reflect on how did I come to do all of this? So my children persuaded me to put this photograph in, much against my better judgment. I was 5 years old, and this dress, I remember vividly. This is probably one of my earliest memories. I loved this dress. I was just learning to read. I had a green dress with some fruit on it that I called my ABC dress. And I had this beautiful pink dress. I don't know whether these are tomatoes or pomegranates. And this I called my math dress. And I recently asked my mum, what was that dress? Why did I call it my math dress? And I found the photograph in the album, so I scanned it and zoomed in. And just zooming in here to show you, any mathematicians in the audience, this is not just a pretty pink dress. Yeah, you hear that? I heard some sound in the audience. So, you know, you see some set theory, you see an integral here. These are advanced mathematical symbols. Now, my family didn't know what these were. I didn't know what these were. I vividly remember being at this birthday party and trying to read the symbols upside down. You know, were they ABCs? I didn't know yet. Now, I was the first child in my family to go to university. My father was a biomedical scientist at a local hospital in hematology. So we had a household where inquiry, asking questions, and reading books was very much part of it. But I did not have a university history in my family. But, you know, looking back, I think how important it is that we inspire children from the youngest age. You know, who invented this fabric? Who thought of making it into a pretty dress for a 5-year-old? And thank goodness that my mum bought it. And of course, this is the advanced mathematics that we use to underpin the physical laws that decode the mysteries of the cosmos. And that, for me, I think is actually quite profound. And since then, of course, as Andrea said, a number of different career steps. This, of course, is big engineering. And I think this is also a theme of this talk, that international collaboration is critically important. This is our research group, and the 2 leading ladies. Science, physics, space science is still really quite male-dominated, but we're blazing the trail here. I'd had my second son just 4 months before that, so it was really phenomenal to win that award. And it was against some very, very important projects. We were a small team. We had limited budgets, but we had clever ideas, and we worked together. And really, our friendship and our collaborations with our collaborators have stayed. I mean, some of these are heads of institutes who came along for a nice dinner too. And then, of course, the invention and the realization of the technology and the engineering. We don't do science unless we have frontier technology. But all of that requires collaboration and different skills. So just wanted to give you a small taste of ESA, because again, I think ESA epitomizes international collaboration and science diplomacy. So we are the only space agency in the world that is multilateral and international in definition. So we have 23 member states and 3 associate countries. Slovenia became a full member of ESA this year, so huge congratulations to Slovenia. It's lovely to have you in the family. And you can see that we're spread across Europe, and we also have our launch site down in French Guiana here. And really bringing 23 countries together, as I do in the science program. The science program is a mandatory program in the agency. All 23 countries have to come together and approve the budgets unanimously every 3 years. And so there's a lot of discussion. Every country's different. The diversity is very rich. Everybody has different priorities, different industries that they want to develop, and their scientists collaborate across national and international borders. So sometimes it can be a lot of work and listening and engagement to move 23 countries together, but when we move together, it's a very, very powerful thing. And the agency was formed 50 years ago. It's our anniversary this year. Space science was really the backbone of the agency. The agency was formed between the European Launch Organization, merging with the European Space Research Organization in 1975. And since then, the agency has grown to really cover all aspects of space, from human spaceflight all the way up to global telecommunications. But the science program itself, the objective is to enable European leadership in frontier breakthrough science and technology and to empower our member states to lead in global space science. It's a very competitive program, and in fact, our missions are uniquely world-leading. And they're also a vehicle and a tool for international collaboration beyond Europe. So we work closely with colleagues in NASA and the Japanese Space Agency and other emerging space nations. And of course, the big questions that we want to answer. We use space in this case. There are ground-based facilities that you'll see later on. And also, I know we have particle physicists in the room. So big science, big equipment, actually asking some of the most fundamental and profound questions that humanity can ask. So what is the origin and nature of the universe? What are the fundamental laws of physics? Are we alone? And I think if we answer whether life exists beyond Earth, that will have profound implications for society, whatever the question is. But I wanted to take you on a quick whirlwind tour of the cosmos. This is the sun, our nearest star. I always say, please don't look at the sun with the naked eye, and certainly not through binoculars or telescopes. You should always protect your eyes. If you go into space and you launch a spacecraft with special filters, this is the view you get of the sun. So you can start to see the sun is more than just a burning ball of gas in the sky, and it's our friend and potentially our foe. Can I point this?
Close the windows.
Ah, yeah, sure. Oh, yeah, it's coming down, huh?
It's hard to get it.
Sure.
Go.
So our sun is just one star. To astronomers, it's a fairly boring, ordinary main sequence G-type star. It's nothing special. But if we zoom out and look at a Milky Way type galaxy, so our star is one star of 200 billion in a galaxy like the Milky Way. This is a view of the Milky Way if we were able to fly above it. We live somewhere about 2/3 out from the middle. And then in the cosmos, there are hundreds of billions of galaxies. So you can calculate how many stars there are, how many planets there might be in the whole cosmos, and what the probability of life beyond Earth is. It's probably significant. And I always like to show a nice image. Now, this is one from the Hubble Space Telescope. That's a collaboration between ESA and NASA. And astronomy, optical astronomy, is very beautiful. We see these beautiful images, beautiful pictures. It's very artistic. But what you're seeing here is a range of physical processes. We see red and dead galaxies. We see new blue galaxies. We see galaxies that are being torn apart because of the gravitational forces between them. So the universe is actually a very violent place. And already I've told you a huge amount of physics without you even knowing it. How do I know that this is a young blue galaxy? Because I know how the blue light is produced, because I can make atoms produce light in the laboratory. I can measure their spectrum. I can measure their color. I can tell you what atoms and molecules and chemicals are in the gas in these galaxies. I know that stars, when they're young, are blue, and as they cool and age, they become red. So a galaxy that's full of red stars is a really old galaxy. It has used up all its gas. It's basically dead. And so you can start to study the evolution and history of galaxies through the universe. And of course, although gravity is considered a weak force, it acts on large scales and is actually a very violent force in the cosmos. And of course, one of the big frontiers of physics is to try to unify our forces. So we have particle accelerators like CERN studying the nature of matter on the smallest scales. And in astrophysics, we look at forces at the largest scales. And yet we don't yet have a unified theory of quantum gravity. And as I say, the main tools that astrophysicists use really is the electromagnetic spectrum. And so the highest energy gamma rays and X-rays that come from the most energetic processes in the universe stream towards Earth. And fortunately, our atmosphere is opaque to these high energy rays. Otherwise, we would all be toasted. So you wouldn't like to be X-rayed every day. I mean, you'd not go to the hospital without any protection. So it's good that the atmosphere is opaque and protects us from that. Ultraviolet light, of course, gets through a little bit, which is why we have to protect ourselves on a sunny day. Visible light comes through. We do like to put our telescopes at the top of mountains so that we have less interference from the atmosphere and we have less water vapor, hopefully less cloud in the way. Infrared, again, is better seen from the sky or space, and then radio waves penetrate right down to the Earth, and that's why we can build giant radio telescopes or networks of radio telescopes, and ultimately we might like to put these into space as well. And then, of course, recently we've also opened up the dark sector and actually studying gravitational waves from space-time itself. And ESA follows a similar pattern there in terms of the emissions that we have. We mostly cover most of the electromagnetic spectrum from space. These are the missions that we've flown in the past, and these have all been groundbreaking in different astrophysics fields. These are the missions that we're currently flying, again, transforming our understanding of the nature of the universe. And these are the missions that we're currently developing in the future, and I'll mention some of these as I go along. Obviously, the detection of gravitational waves with ground-based gravitational wave detectors back in 2015, Nobel Prize-winning discovery, has now opened up a new window, and in 2035 we will launch the world's first ever space-based gravitational wave interferometer. The other reason we go to space is not just to get a better view of the cosmos, but to actually go to somewhere. We obviously can't go to other galaxies or to other stars because they're too far away, but we can travel through the solar system. And again, the same scheme, missions that we've flown in the past, missions that are in the sky right now, missions that we're preparing. When you fly into the inner solar system, your spacecraft speed up because you're going towards the sun, you're falling into the gravitational potential of the solar system. So the big technological challenge is to put the brakes on the spacecraft and manage to get captured by the planet that you're targeting. For example, we're on the way to Mercury at the moment. When you go in the other direction, away from the sun, out into the outer solar system, so out towards Jupiter, you have to speed up. And we don't have rockets that are powerful enough to take us straight there. So we have to use gravity and all sorts of clever ways to slingshot us and speed our spacecraft up. So you see that gravity sits in everything, not just the science, but the technology and how we use it as a free energy source. And really, again, I'm always very humbled when I look at the missions that humanity has done. The Cassini-Huygens mission this year, we celebrated the anniversary, 20 years of landing on, and it still is humanity's most distant landing on a distant moon. This was a mission between ESA and NASA. And this is not actually rocks, this is actually a frozen riverbed, and it's frozen methane. And this descent probe was expected to crash and smash to smithereens. Do I have any space scientists in the room that build instruments for space missions? No, okay. So just imagine if your job was to build something that was to be destroyed. And you spend 10 years putting all your love and attention and ingenuity into something you're told, don't worry, it's not going to survive. You're doomed. It didn't. It landed, measurements were made, and apparently the surface of Titan is a bit like creme brulee. Crispy on the top, soft underneath. The other wonderful mission that we all know, just as citizens following the news, was the ESA Rosetta and Philae mission. And these are real images taken as the descent probe landed onto a comet. So this comet zooming through the solar system, the spacecraft went out, chased it, went to a very complicated orbital pattern, and landed a little lander on the surface of the comet. I think that's incredible. So if humanity can do this, we can pretty much do anything. Space missions, of course, all operate in a very hostile environment, so it's quite different when you work with space and ground technology. Everything has to be protected. So out there, it's extreme temperatures, it's extreme radiation, it's magnetic fields, it's charged particles, and the sun is probably one of the most extreme environments. Just as a scientist, I just love this movie. So this is our Solar Orbiter mission. It's the highest resolution images of the surface of the sun. Again, you can't see this with the eye. We see the sun when it goes into outburst, but now we're understanding the sun when it's quiet as well. And you can see the phenomenal structures in the middle. You'll see a tiny little mini flare. So as I say, it's not just a ball of gas. It's incredibly complicated. And the reason I'm showing you this is not just because solar physics is important and it's important to protect the Earth, but because there's going to be a theme that runs through my talk. Hands up, any students in the room? Okay. So a little bit of advice to students. Now, you all look very bright and attentive, and that's good. But sometimes you might be studying hard and you might be a bit sleepy and you might fall asleep in the back of a seminar. So you wake up and you think, oh, did my professors notice I've fallen asleep? And your professors will always sit on the front row and you'll always sit at the back, I know that. And your professors will all be asking questions. I'm looking at a colleague here who I'm probably at the end may say, I have a question, it's more of a comment. No, he's not going to say that, I know. But all your senior colleagues are going to be asking good questions, and you put your hand up and look intelligent, which you are, and you'll say, but what about the magnetic fields? 9 times out of 10, the speaker will say, oh, magnetic fields are very hard. Oh, you've figured, I was trying to keep this secret, but I've neglected the magnetic fields in my simulations, or I can't measure them in my experiment, or I don't yet know how to deal with them. Little word of warning, when I give a talk, it's all about the magnetic field. So if you say that, that's the 1 time out of 10 I'll know you had a nap. which is fine. You study hard and you need to take a rest. So I hope to keep you awake throughout my lecture. But of course, magnetic fields in the sun is what's critically important, and that's what actually determines some of these energetic outbursts. But what's really exciting about Solar Orbiter is for the very first time, we're changing the dynamics of this spacecraft, and we're moving out of the plane in which the Earth orbits the sun, the so-called ecliptic. And dynamically, this is very hard to do. We don't have enough power on the spacecraft to do that. And actually what we're doing is we've done a slingshot around Venus. We've used the energy of going around Venus to slingshot the spacecraft up and out of the ecliptic. And we're still making this maneuver. Ultimately, it will be 33 degrees above the plane in which our planet orbits the sun. Why are we doing this? So that we can give humanity the very first view of the top of the sun and the bottom of the sun. Never has humanity ever seen the poles of the sun. Ulysses tried, but melted. So this is not Ulysses. I mean, I'm saying Ulysses the myth rather than the spacecraft. And so this is really incredibly, I don't know, there isn't a word to describe the fact that humanity is able to fly out of the plane of the solar system and look at the top and the bottom of our own star. So you can see these gravity assists will continue to do that until we're nice and high up. We had the very first view of the data. It takes several months to get the data back. They've been streaming down. Sometimes the spacecraft is on the far side of the sun and we lose communication, then it comes out and it streams the data down. And so you can start to see the view as we tilt out. We're starting to zoom into the bottom, and these were the very first images that came off the spacecraft in July of this year. And the reason this is important is because sometimes the sun is very active and it produces lots of radiation and charged particles at solar peak, and then it goes into a quiet period and goes into solar minimum. This happens about every 11 years and we don't know why. And we're now starting to get the first glimpse of the magnetic field structure at the poles of the sun, currently at solar maximum, and will continue to do that as it goes into quiescence. So overall, over the last 50 years, with the input of our science community and scientists and engineers and industry across Europe, we've built this very, very comprehensive space science program. At the moment, obviously, our budgets are significantly smaller than NASA's traditionally have, but we have the two world's largest and most significant space science programs in the world at NASA and ESA. We cover everything from near-Earth heliophysics, so how the sun affects the Earth, all the way out to the nature of space-time and fundamental physics. As I say, 50 years of discoveries, and I just put these panels together. I'm not going to talk through each mission. I had a colleague who was an expert in public engagement, and she once gave a presentation on how to give a good talk, and her title of her talk was, "Nobody Cares About Your Satellite." So there's a challenge. I care about our satellites, but it's not the satellite, it's the science that it enables. It's the sense of adventuring. As I say, the very first close-up view of Comet Halley, looking at the high-energy universe in 1975. This was when I was in my maths dress, and ESA was already looking at the high-energy universe, so I feel very humbled to be in this role now. Hipparcos, some of the most precise measurements of where stars are in our Milky Way. Ancient scientists and maritime navigators use the stars to map where they are on the planet, and this now we do from space, and I'll show you shortly how important that is. And basically it goes on and on, whether we're looking at the hottest gas in the universe that produces X-rays, whether we're looking at how the sun impacts the magnetic field of the Earth that protects us from dangerous particles from space. We've been orbiting around Mars now for 21 years. I can tell you all about the water, the ice, the frost that forms each day on the top of Olympus Mons, which is the largest volcano in the solar system. Rosetta, as I say, landing on a comet. And then right out to Planck. Planck was a cosmology satellite. It measured the ripples, the tiny little quantum fluctuations at the beginning of the universe and the Big Bang, and now added up the census of everything in the universe. So we now know what the universe is made of because of Planck. Gaia mapped 2 billion stars in our own Milky Way, and I'll show you that again. And then it goes on. And then we have future missions that we're planning at the moment. SMILE will launch in the spring of next year to study this incredible impact the sun has on the Earth. A little bit after that, we'll launch Plato, which will look for Earth-like planets around sun-like stars. So we're looking for Earth 2.0. Ariel will complement that. That mission will actually study the atmospheres of 1,000 extrasolar planets. So we'll now start to do climate change on other worlds. And then Comet Interceptor really is a successor to Rosetta. And this nifty little mission will launch in 2028. It will wait in deep space for a pristine comet to come through from the edge of the solar system. It's never been in the inner solar system before. It will chase it. It will launch itself from that position in deep space. It will chase the comet, launch 2 daughter spacecraft, study that ancient comet, and go off and do some other studies as well. And what we really want to understand is the origin of the solar system, which we now think is twice as big as we used to previously think. And then the thing that we're really working on at the moment is to develop our next big flagship mission. We're on our way to Jupiter with a mission called JUICE, but this is a mission that will launch in 2052. I know that sounds really far away, but the cosmos sets our deadlines. We have to launch in 2043 because it takes 9 years to get there, which means all of the technology has to be invented and ready to build onto the spacecraft by 2034. Next year's 2026. That's really only 8 years. So we have to invent a world-leading battery that can fly for 7 years asleep, wake up in temperatures that methane freezes, and operate happily on the surface of an unknown planet for a month. Whoa, we've got a lot of work to do. We need to miniaturize the instruments, so we're working with the biotechnology industry, and this will be humanity's first ever astrobiology mission landing on a distant world. We don't know what the surface is of Enceladus. We have observations of it. It might be snow, it might be ice. We don't want our laboratories to land and suddenly fall into an avalanche and disappear. So we'll use lots of autonomous imaging and lots of artificial intelligence and machine learning because it takes too long to communicate. We can't fly it live. And this is what we're asking our ministers to support in November when they come to Germany for our ministerial conference, when they set the budgets of the whole agency for the next 3 years. We're asking them to set the level of resources for the science program at the right level to help us to begin next year the technology development for this mission, because the race is on and we need to get there. But we're not the first people ever to look at the sky. And I've given you this kind of high-tech tour of the universe over the last 50 years. But when we look back 15,000 years ago, ancient man was looking at the sky. And these are some beautiful cave paintings in Lascaux that were found in the 1930s. I think a little boy had fallen down. And archaeoastronomers and archaeologists studied these incredible cave paintings. And there's many paintings of livestock. There's very accurate depictions of antelope leaping. And you can imagine this might have been an ancient movie theater. It's very dark, obviously, in these caves, and you could imagine an ancient tallow candle. Maybe this was where everybody went on a Saturday night. This was your IMAX of Cro-Magnon era. But it's an incredible place, and if you take a candle and you do that, it makes it look as though the antelope are leaping across the sky. But for many years, people thought this was a very nice picture of a bull, until this German archaeoastronomer came along and said, this is not a bull, this is the constellation of Taurus on the sky. This is the Pleiades star cluster, and this is the belt of Orion. Whew. Now we have an ancient planetarium. It's not just a movie theater. Now, I have a hypothesis, and it's just a hypothesis because it's not my area of expertise, but I think that's not the belt of Orion, because Orion has 3 stars. And I wonder whether that is the course of a planet moving across the night sky over about the course of a month relative to the fixed background of stars. And so this is the first study of planetary motion, I would say, and therefore the birth of time domain astronomy, which is what Andrea and I and our groups have pioneered for the last 20 years. So it's quite an old subject. But ancient people would have looked at the sky. They were looking at change. Change is something that human brains notice. If something stays the same, you start to not notice. So this would all have stayed static, and this would have changed. And that's my crazy hypothesis. Why is it important? Because that's what ancient astronomers have done for a long time. They've studied how things move on the sky. Copernicus, back in the 15th century, brought up this heretical idea that the sun was the center of the known universe. At that time, everybody believed the earth was the center. Naturally, you look up at the sky, you think you're the center of the world. And he came up with this sun-centered cosmology, which turns out to be true. Galileo came a little bit later, and he was really a modern adopter of technology. So the telescope had just been invented, and he pointed the telescope at Jupiter. And for the first time, he saw the moons of Jupiter. He saw moons orbiting another world. And of course, as you know well the history, Galileo got into terrible trouble with the church, because the church's teachings at the time was that the earth was the center of the universe. And Galileo said, I can't deny my eyes. I have the scientific evidence, and the evidence points to something else orbiting around. So the sun then centered cosmology becomes real. Kepler came along in the 16th century, and as biographies are written, he went to Tycho Brahe's house, and Tycho Brahe was a Danish gentleman, amateur astronomer, but he built telescopes. He liked to build things, and he liked to study where the planets were on the night sky, and he mapped them down, position, date, time, all of his life. And so as the story has it, his house was stuffed with all of these observations. Every night he wrote numbers down. So I always think of Tycho as the beginning of the big era of data science. But he passed away, and you can imagine his poor wife, she's got all this rubbish coming out of the drawers. What does she do with this? And young Kepler comes along, and he's an enterprising young man, and he says, I'll take that rubbish off your hands, because Kepler knew the value of data. And I think the big AI companies know the value of data. So he took the data. Tycho had been trying to find a pattern in the numbers and didn't find a pattern, but Kepler got lucky. He did. He obsessively analyzed these data, and he found a pattern in the data. And that was really the discovery of Kepler's empirical laws of planetary motion. And so what he did, he had a mathematical equation that told you actually where the planets were in the sky, and what was revolutionary, he was able to predict where the planets would be in the future. So that must have felt quite radical. He, for me, I think, is the birth of empirical science, because the goal of science is to try to find a pattern and predict the future. What he didn't know was why that pattern worked and why he was able to predict the future. And it wasn't until Isaac Newton came along and discovered the universal law of mechanics and gravity that we now understand the way they move. They orbit around the sun, and the gravitational attraction between the sun and the planet is what causes it to go around in its orbit. So really, observational astronomy led to the fundamental discovery of the laws of physics that govern our everyday lives today. But that wasn't quite enough. So Newton's law of gravitation really persisted as the theory of the day for several hundred years. And then coming up to the 20th century, this young man, Albert Einstein, was sitting in the patent office imagining things about the universe. And he was struggling to develop his general theory of relativity. And he worked with David Hilbert, and particularly Emmy Noether, who was a mathematician at the University of Göttingen. Now, at that time, women could not be paid. And again, the story runs that she was asked to work in the basement of the physics department because the men were on the floors above. Do we have any physicists in the room? You can put your hand up, don't be embarrassed. I'm a physicist too, it's fine. There we are. I think you don't put the women in the basement anymore, and I think you do pay your women professors, so we have seen progress. But Emmy was very clever, and I think Emmy really underpins the whole of modern physics. And I'm embarrassed that, having gone through my career, I hadn't heard of Emmy Noether, but when I speak to mathematicians, she's a hero for them. But anyway, it was really Emmy Noether and the conservation laws and symmetry that helped Albert to figure out how to make his theory of general relativity work. And this is the equation. And what this simply put tells you that space-time tells matter and light how to move. You can see it here, it's showing. Matter and energy tell space-time how to bend. And you put the two together and you understand everything. Now, if you expand this mathematical shorthand, it's actually 10 independent, second-order, nonlinear partial differential equations. So for the rest of the lecture, we'll go through those equations, okay? You laugh. I'm serious. I'm not serious. But actually, there are 3 analytical solutions that have been found very early on for those equations. And since then, for the decades since, scientists have been crunching these equations in their computers and finding approximate numerical solutions. But there were 3 analytical solutions. And they made 3 very important predictions. The first was that the universe should be expanding. Now, in Albert Einstein's time, that sounded strange, but of course in the 1960s, 2 engineers at Bell Labs in the United States found this weird static in their detectors, which they thought were pigeon droppings, and it turned out to be the dying embers of the Big Bang. And so they proved that the universe was expanding. So that was the first prediction. The second prediction was that black holes should exist in nature. In theory, they should exist in nature. So for probably 50 to 80 years, the concept of black holes languished in the mathematical literature and sometimes made it into Hollywood in later times. Now you ask any astrophysicist, founded our careers studying black holes. Stellar mass black holes, a few times the mass of our sun. Supermassive black holes, 1 million to 1 billion times the mass of our sun. And we're now seeing all sorts of medium-sized black holes that we don't know how they form. So simply put, a black hole is a region of space inside which the pull of gravity is so great nothing can escape, not even light. And so you immediately are thinking, I can see it on your faces, well, if you can't see them, how do you know they're there? This little equation at the top will tell you your Schwarzschild radius if you were to take your mass and squeeze you down to the size of a black hole. So you have to take your mass in kilograms, divide it by the mass of the sun in kilograms, which is 2 with 30 zeros after it, and multiply by 3. I mean, astronomers like to be precise. The 3 doesn't matter. You'd be really, really tiny and you'd evaporate very quickly, so do not turn into a black hole, please. It's not fun and it's painful. And so how do we know that there are black holes if we can't see them? So there are 5 different ways that we can prove if a black hole is there. First of all, cosmic indigestion. I'm going to be quite vulgar now. Anybody got or had young children in their families? You know, if they get sick, ever? Have you ever known a small child? Have you ever overfed a small child? Do you understand the concept of bipolar outflows? Yeah, okay. So this is what we do to black holes, okay? Now, everybody thinks, the popular literature says black holes are great big cosmic vacuum cleaners. They're not. It's actually very hard to stuff material over the event horizon of a black hole because we have what's called angular momentum. Stuff tends to go round things in the cosmos. So it's very difficult to feed black holes. When you feed them, they do grow a bit. And what we see in the Universa, the idea was that if you try to overfeed a black hole, and again, hands up my students, you've had some magnetic fields, then interestingly, the material cannot just be gobbled up, it actually gets ejected out. So you overfeed a black hole, you can look for the signs of cosmic indigestion. You can look for the gravitational pull, as the same way as the Earth orbits around the sun and the solar system planets are held in place by the gravitational pull between them and the sun. You can do the same thing around a black hole. If you're orbiting around a black hole, you're going to feel quite a pull. We can look for the catastrophic birth of these black holes, which is what we did in our gamma ray burst group. When a black hole collapses, it puts out a lot of energy, so you can look for that. And you can look for what happens when black holes crash together and they make space-time ripple, like throwing a stone into a pond. Ripples in space-time were the third prediction from Einstein's equations that there should be gravitational waves. If space-time is perturbed, those ripples should be detectable. And again, in Einstein's time, the engineering was impossible. There was no way this could be done. 100 years later, we've done it. And the last one is to try to make an image of a black hole event horizon. Now we sound like science fiction. And I've used this slide over the last few years in a number of public talks, and every time I gave a talk, I mean, I started with maybe the bottom three kind of grayed out because, well, it hasn't been achieved yet. Every time I gave this talk, I had to update the slide because the pace of discovery in the last 10 years has been so fast in black hole science that we've achieved all of these. And I wanted to show you this on the bottom. Hands up, anybody who's been to see the movie Interstellar. Okay, keep your hands up. If you are not a physicist, okay, and if you went to the cinema with a physicist friend.
Where is?
Oh, the hands are going, okay. First of all, don't go to the movies with a physicist to watch Interstellar. If you do, ban them from speaking. Because they're going to, well, that's not quite right, but I don't think. Actually, it was a wonderful film. It's a Christopher Nolan film. There's a lot of very good physics in this film. And actually, the company that did the graphics, a British company called DNEG, they actually worked with astrophysicists at Caltech to put proper gravitational physics. And they wrote this very serious research paper in classical and quantum gravity. Proper research paper. And what's interesting when you speak to the filmmakers, they have good physicists in their company, they said, well, from the perspective of a camera, I need to be able to film near a black hole. The physicist was saying, you can't do that because this is what gravity is going to do to you. And so this is kind of a simple representation of, you know, the space-time around a black hole, and then you add some relativistic effects, and then you add gravitational redshift, and this is what the physicists got. Now, Christopher Nolan apparently looked at this and went, it's not very pretty. So he picked this one. So even in Hollywood, black holes wear makeup. But there's good physics under there, and then there's artistic license, which is also wonderful. It's a superb film, and I love it. So cosmic indigestion. I've told you all these things, now I have to prove it to you because I'm a scientist. So what is cosmic indigestion? So this is a galaxy. This is one of these red and dead galaxies, a big ball of stars, and the stars are orbiting around. And this galaxy cannibalized a Milky Way-like galaxy. Milky Way galaxy is a disk of stars and gas that orbits around. Younger, lots of gas in it. And the gas and the dust actually is this dark patch across here. It's absorbing the light from the background stars, and that's why you see this weird picture. You can see this in the southern hemisphere. It's called Centaurus A. And that's what you get if you use a camera with multicolors. So it's an optical photograph in multiple colors. If you had a very sensitive iPhone, this would be what it would look like. Now, I showed you the whole of the electromagnetic spectrum. So if we now point our radio antenna at this is what we get. So this is false color. This is a plasma of charged particles, probably electrons, also protons, maybe positrons, spiraling around, I hate to say it, magnetic fields. These are the largest continuous fluid flows known in the universe. We actually don't know why they're physically and dynamically stable. They're energetically so powerful that they cannot be produced by normal stellar processes. It can't be stars powering this. And it was actually the theorists back in the 1970s that quickly understood this has to be due to black hole-driven accretion. So these plumes are driven by the energy extracted from material falling towards a black hole and not being swallowed. So it's a little bit like, and apologies to those who've got electric cars and don't understand what this picture means, but what we're trying to do as astrophysicists is studying the exhaust material from the black hole-driven central engine, and all we have is the light that we get from that, and that's what we try to decode. And actually this has been a remarkably successful model. So the infalling material has angular momentum, it gathers in an accretion disk, the material spins faster and faster, it heats up, and then the magnetic field focuses and ejects these giant plumes. And our new Athena mission that we're preparing at ESA at the moment will launch in the 2030s to study this hot gas across the whole of the cosmos. It will be the world's largest X-ray observatory. It's absolutely humongous. We need a 2-story building just to build the telescope tube, so that's going to be very exciting. Look for the shadow of an event horizon. This again was science fiction until we decided how to do this. So this is radio astronomers taking all of their antennas around the world. This is the ALMA millimeter wave telescope, about 66 dishes in the Atacama Desert, high up in Chile. Very, very dry site, 16,500 meters above sea level. And all of the groups that ran these observatories decided to collect them all together and use the Earth as a giant telescope. So when you connect all of these antennas around the world and the Earth rotates, it acts as a giant radio telescope, which gives you phenomenal detail. And they were able to test this theoretical prediction of what space-time would look like around a black hole, and this was the actual observation. Now, this is a giant old galaxy. This is a plume of plasma coming out here, and looking right down into there, there's this shadow of the event horizon of a black hole. We are living this, in our lives right now. We're seeing this technological development. So putting it all together, we understand that we have a black hole at the center, we have this hot material swirling around, we're disturbing space-time, we have magnetic fields extracting these plumes. The plumes produce X-rays, they also produce radio images, and that was the little jet that I showed you in the visible photograph, and all of these charged particles are being spewed out of this black hole-driven central engine. We're now building facilities on the ground, for example, the Square Kilometre Array. This is an international collaboration. The headquarters are at Jodrell Bank Observatory in the UK. This is being built in South Africa and Australia, and it's a global collaboration between European member states, Australia, Canada, South Africa, India, China, and it will be the world's largest radio array and will completely transform our view of the cosmos. Now, the second way you can measure black holes is actually by looking for the gravitational disturbance of them directly, because you could say indigestion is a bit circumstantial, you have to trust the physicists have done their calculations properly. Do you have any direct proof? So it's now, because of the technology development we have in adaptive optics and being able to peer through with great detail, these were observations made by, there was an American group and also a German group, again, Nobel Prize-winning discoveries. And what you see here are stars at the center of our own galaxy, looking in the infrared. And if we zoom in, you're actually seeing this. You can see it's over about a decade. This is year in the top. Where's the black hole? Did you spot it? Should I do it again? And what you're looking for here is when the star goes round, it's going to feel the gravitational pull of the black hole, and it's going to get whipped around the corner, just like our spacecraft are being whipped to speed up and slow down in the cosmos. I put the cross where the black hole is. I've given you the answer. But these are real stars, feeling the pull of gravity at the center of our own Milky Way galaxy. We go in here it goes, 10 light days, woof, round the corner. That's phenomenal, isn't it? It can't be anything other than a black hole because it's 3.3 million suns crushed into a small area of space. If it was just a star cluster, it would have evaporated by now. 15 billion suns per cubic light year. That's a lot of mass. We now think that there are supermassive black holes at the heart of all big galaxies in the universe. We think they're very integral to the formation and evolution of galaxies, but we actually don't know whether the black hole seeds the galaxy or the galaxies smash together and grow the black hole. We have a kind of a chicken and egg problem. And in fact, this is a very nice example from the Hubble, the James Webb Space Telescope, which again is a collaboration between ESA and NASA. This is the most distant galaxy in the universe, and these galaxies are already very massive. The universe is too young. These massive galaxies should not have had the time to form. They should not have had the time to form black holes. So there's something very uncomfortable that we don't understand yet about galaxy formation and evolution. Now, the next way I said was what happens if you catastrophically form a black hole. Again, I'm going to go back because there's a lot on this slide. So what you're seeing up here, this is a gamma ray detector looking at the whole of the sky. This bright patch along the middle is actually the high-energy gamma rays that come from all the energetic processes in the plane of our Milky Way galaxy. So it's like we're in the disk and we're looking through. And the rest of the sky is the rest of the universe. And what you see here is the brightness in gamma rays, and you suddenly get this very bright flash, and it's only 10 seconds, and it's so bright, you'll see, that it swamps the entire detector for a fraction of a second. Watch the image, bang! You see, it went off up here, it was so bright it swamped the whole of the detector, and then it was gone in just a matter of 3 or 4 seconds. And back in the 1990s, the Compton Gamma Ray Observatory looked across the night sky, and it was seeing these flashes all over the place. There was no preferred direction for them. And there was a huge debate among scientists in the 1990s. These are so bright, and they're evenly distributed across the sky. We can't predict where they'll happen, when they'll happen, but they're quite evenly distributed. They must be in the halo of our own Milky Way galaxy. They cannot be cosmological. So half of the scientists said they're very far away, and the others said, you're crazy, they're in the galaxy. And there was a great debate that was held in Washington. Lord Martin Rees chaired the debate, and the camp that were thinking they were nearby won the debate. And I once said to Lord Rees, why did they win? Because I'll give you a spoiler alert, they were wrong. And he said, because they were better speakers. So, lesson to scientists, go in your media training. But the point was they were so bright, you couldn't imagine, something nearby seems bright, but if you put them at a distance, then they have to be intrinsically powerful, and it seemed impossible physically to do that. But a European satellite called Bepi-Sachs made the first X-ray detection, and that light lasted a lot longer. They could get a better localization, and then they could tell the optical astronomers where to point their telescopes. So 1997 was the first optical detection of a gamma ray burst counterpart, and that was really the basis of how we built our Liverpool group. So what we think happens is we think a massive star, 200 to 300 times the mass of our own sun, gets to the end of its life. It stops burning hydrogen, and it can no longer support its own weight, so it collapses catastrophically into a black hole and blasts its outer regions off. In doing so, it's spinning, has an accretion disk. Students, it has a magnetic field, yeah. We don't know that yet, and that's what I'm coming to that in the talk. We proved that with our observations, but the hypothesis was the magnetic field does something to spew these jets off in a mini version similar to the supermassive black holes. So in Liverpool, we were building the world's largest fully autonomous robotic optical telescopes, originally to look at novae, which are sort of slowly changing stars. And NASA at the same time was developing a satellite called SWIFT, and the idea was that it would be able to look across most of the sky, catch these flashes, because you don't know where they're going to happen, and send an accurate position notification down to ground-based astronomers. So what we did was, in building these 3 robotic telescopes, we were given, within the Institute, some guaranteed time to be able to develop our software and our instrumentation. So we wrote software that took the signal directly from the satellite in seconds and immediately told the telescope, stop what you're doing and go and look over at this important point and make some observations. And at that point, first of all, we were taking images and trying to find the optical counterpart. We were waking up in the middle of the night. The very first time I sent a circular, I can see Andrea smiling, to the so-called gamma ray burst circular network. And I'll tell you how ferociously competitive it was at this time. My newly born son was asleep. It's about 5 o'clock in the morning. The telescope in Hawaii, I couldn't figure out the date line. Looking at my colleague from Hawaii here and thinking, is it today or is it tomorrow? Is it yesterday? And we named the GRBs by their dates. So 25/12 would be Christmas Day in 2025. So very boring, but we know exactly when they happened and what we were all doing with our families. And I sent my message to the exploder, and it said, your email will be distributed to 1,004 scientists. And I went, oh, I hope it's right. It wasn't right. I got the date wrong. I was on the wrong side of the date line. So I thought, I'd better send a correction. And I typed the correction, and I sent the correction to the exploder. And in between sending that correction to the exploder and it being exploded, a scientist in Hawaii emailed me and said, you got it wrong. Now, why is that important? It's important because when you write to a scientist, I would have to cite that scientist in my next circular. And I wrote back with a screenshot and said, already sent the correction. It was a very exciting, very ferociously competitive time. Because these were big frontier questions. We didn't have much money. We wanted to build a new instrument to study magnetic fields. Because the real scientific question, apart from being the best, apart from being first, apart from finding the first counterpart, we also found the faintest ones, and we were able to really pioneer what the distribution of brightnesses and positions were for these things. The big fundamental question our group wanted to answer was how are they powered? And in particular, are the magnetic fields important? There were 2 big competing theoretical models, and we figured out we'd be able to distinguish between the two. And it's not often in astronomy that you have a very clear theoretical question that you can build the equipment for and test and rule out the theory. One was that these materials were just kind of pushed out by energy. The other was that magnetic fields focused and accelerated the material to speeds close to light. And then when the beam points to you, it's a bit like my laser pointer, you see a bright flash. There are many that are pointing away that we never see. We only see a small fraction of them. Now, as I say, measuring and detecting magnetic fields in the universe is probably one of the hardest technical challenges. And in fact, the square kilometer array, one of its key science questions, which is yet to be realized, is the nature of cosmic magnetism. So we were very far ahead of the field 20 years ago. As I say, we didn't have much money. We went up to see Dr. Dave Clark at the University of Glasgow, and he'd invented this nifty kind of stellar polarimeter, but he'd never used it in anger on a telescope. So we used year-end teaching budgets. I'm looking at your senior professors here. There's always a little bit of money if you ask nicely. Don't ask for a lot. We asked for permission for the engineers in the institute to be able to refocus their work a little bit over the summer, and we built the world's first best real-time polarimeter. And what that does is it looks at the light. It doesn't just look at the brightness of the light and how the light changes, but it looks at a special property called the polarization. And if you're driving home late at night, the sun's low in the sky and the road is wet, that glare that you get is from polarized light. And if you put your Polaroid sunglasses on, it takes the glare down. So we were really not just trying to catch the light just seconds after the collapse of the black hole, we were trying to measure the glare on the light. That's how hard this experiment was. And so we actually developed 3 different generations of our Ringo polarimeters. We were in Liverpool. I'm sorry, Ringo was not really named after the Beatles. I would love it to be so, but the very first invention, we actually made rings on the CCD because we put sunglass material, we glued it to a deviating prism, and we spun it at 500 revs per minute, 24 hours a day, and we caused some new company to develop their technology and grow their profit margins, which was also a great and nifty consequence of our questing. So what you see here is probably one of our most exciting results, and we did many of these. This is the sky before, so you can see these stars. You can see this pattern of little stars here. You see the same pattern here. And you see that here there's nothing, and then overnight this thing went bang. It was very, very bright. Our telescope moved automatically, started making the observations, started to stream the images. We knew this. We sent our circular out to 1,000 astronomers saying, we'll give you a hint of what we found. There's a lot of negotiation in science. We'll tell you the position of the optical counterpart. We'll give you the brightness, and we're continuing to make observations. And our polarimeter made its measurements. And in fact, the light was polarized by 30%, and that's very, very high. Stars have that polarized glares about 2 or 3% if you scatter the light through dust. If you have magnetic fields, you have charged particles spiraling around those magnetic fields, you produce high polarization. So this was the highest polarization ever detected and still remains a record, 8 photos per second, and it was about 160 seconds after the burst. Still remains the record, and it's the definitive proof that we have large-scale ordered magnetic fields. We obviously published that in Nature. And we also measured the time evolution of it, so we could see the magnetic fields rotating. The reason you do this early is because it's the point when the black hole collapses, when the magnetic fields are still encoded in the fireball light, and after that it gets messed up because it crashes into the material roundabout. So speed was of the essence. Real-time physics in the middle of the night. This is what we think they look like. Again, an analogy with the galaxies. We think the black hole forms. We think we have these spirally magnetic fields, and the material spewed out. And when it points directly to us, we can measure those magnetic fields. So that was very exciting, very important. And then, as I say, in 2015, the final piece of the puzzle comes in, where the first detection of gravitational waves was made. That's the sound of a black hole forming and causing ripples in space-time, which again I still think is amazing. The lower signal is actually the gravitational wave signal turned into an acoustic sound. The higher pitch is just to help you to hear it. False alarm rate, less than 1 event in 203,000 years. It was a very, very significant result. It was 2 black holes, one about 30 times the mass of the sun, another similar. They crashed together. They produced a bigger black hole of 60 solar masses, and they released the rest mass energy equivalent of 2 black holes, which is the most energetic process, and it's now beaten our gamma ray bursts. So that was very fundamentally important. It proved Einstein was right, and it opened up a brand new observing window in the universe. And a couple of years later, this gamma ray burst happened, and it also coincided with a gravitational wave. So this again is this chirp. If I played it, it would be a very long time of nothing, and then you'd hear whoop at the end. Boom, that was probably two neutron stars colliding. A neutron star is the dead remnant of a collapsed star that hasn't fallen into a black hole, and a sugar cube of the material weighs about the same as a medium-sized mountain. So this is the densest material in the universe. So this was actually my birthday. And it was the first time in, I think, 10 years I'd switched my phone off. And then the next day I switched it on and there were lots of signals. So this is very, very heavily embargoed. And our dear colleagues in the media, journalists, were calling me up and saying, did anything exciting happen on the 17th of August? And I was like, yeah. What? It was my birthday. Oh, you're no use. We're not going to talk to you anymore. We want to hear real news. But it was very exciting. We had a big press release. What was important for gamma ray burst science was at the same time as this gravitational wave being detected, there was a tiny little gamma ray flash detected by NASA's Fermi satellite. And the reason this was important was because another way you can produce a black hole from a stellar gamma ray burst is by crashing two dense neutron stars together. They spiral together. They're too massive to survive, and they fall and collapse into a black hole. And we thought it would be another 10 years before we would prove this. So we got very lucky. That was a gamma ray flash 1.4 seconds after the gravitational waves. So it tied these theoretical models together. Scientists around the world also put their optical telescopes on. It's looking for like a needle in a haystack. There's a lot of galaxies out there, and you're trying to find this stellar system in those galaxies. This is just the local web of galaxies in our local neighborhood. And in fact, the galaxy was found. It's here. That's a real photograph of the galaxy. And that's the gamma ray burst, and that's the gravitational wave merger, and that was the birth of a new black hole. This is what we think happens. We think two neutron stars merge together, and they spin faster and faster and faster, and at the point of coalescence, they're spinning at speeds close to the speed of light, and that really is a universal speed limit. They crash together, and they produce these phenomenal jets, and these jets point towards the Earth, and we measure them with our telescopes. And we think that something like a third to half of all the gold that we know in the universe is formed in the merger of neutron stars. So if you have any rings on, it's probably cooked up in a collision like this. So that's kind of cool. We now are finding black holes all over the place. You can go to this nice little web page if you want to sort them in different ways. You can find out all the information. And when scientists find a new one, they'll put this on this diagram. You can look up the information. The scientists provide all the information for you. I've just done this and recorded myself moving across the screen. You can find everything out that you need to know about it. It's a very nice web page. You can find the small ones, you can find the big ones, you can see if there's an electromagnetic counterpart. So this is a whole brand new area of astrophysics that has opened up. And, I think personally for me, this career journey, the wonderful people that I've worked with, sometimes on a shoestring budget, sometimes in times of crisis, sometimes coming to Slovenia and having our research workshop in Bled. Where could be better? Bled cream cake, yeah, kept us powering, wrote us our nature papers. And this was a paper that I finished just before I joined ESA with my student and postdoc, Nure Jordana Mitchens. It was such an exciting result. And we'd found this short gamma ray burst. We were pretty sure that we now know that these are the merger of neutron stars. But what was unusual about this is we were measuring the optical light and its performance and the polarization. This thing didn't immediately collapse to a black hole. And in fact, it was spinning very, very fast. It had magnetic fields that were extracting the energy. And it lived a little bit as a supermassive neutron star beyond the mass limit that it should exist. And we actually saw it collapse into a black hole in real time, which was phenomenal. Obviously, we did a lot of checking of our data. So we expect that in upcoming surveys with, for example, the Rubens Observatory and NASA Grace Roman in the future, there should be thousands of these supermassive neutron stars caught in the act of collapsing and forming a black hole. Gaia is our ESA mission that we retired this year, but it's actually studied 2 billion galaxies in the Milky Way, where they are, where they're going, and slight wobbles in their trajectory have helped us to find 156,000 asteroids in the solar system, 350 of which have moons orbiting them. So we do solar system science for free. This is not an image, this is actually a dot-to-dot picture. So every pixel in this map is a star for which we've measured the properties, the brightness, the position, where it's been and where it's going. So we now understand a lot about the formation and evolution of our own Milky Way galaxy. But for black hole scientists, and you can look at there's always superlatives with ESA missions, I love it. Trillions, billions, millions, fastest, biggest. But actually for our black hole scientists, the reason it's been so transformational is because after, you see the timeline here, after 2,000 years of astronomers and navigators painstakingly measuring the position of stars on the night sky, We went to space and an absolute revolution in precision astrometry. This is the space revolution starting here. So 1,000 times improvement in 2,000 years, a 10,000 times improvement in 25 years. And this is important because we now have a very precise measurement of the celestial reference frame, and we use that for our navigation satellites above Earth. So something esoteric helping you drive your sat-navs. But what Gaia did, which I think for me now again is opening a brand new world, we know that at the center of the Milky Way we have a supermassive black hole, because I showed you it pulling the stars around. But what we didn't know was out in the galaxy there are these smaller black holes, 10, 20 and 30 times the mass of the sun. Wow. And we think the Milky Way may be full of all of these floating. We have 2 more data releases that the scientists are working on, and we expect to find many more of these black holes. So there's an awful lot of black holes in the universe that we didn't know previously existed. And the things that crash together to make these black holes, as I've shown you, will be the cosmic calibrators for our LISA mission. So this will be the world's first ever gravitational wave interferometer. We'll fly 3 identical spacecraft. Each spacecraft has a gold test mass on that is in free fall, so it doesn't know it's on a spacecraft. And those spacecraft will fly around the sun on an Earth-Sun orbit with a distance between the spacecraft of 2.5 million kilometers, and they'll be precisely aligned with lasers to detect ripples in space-time smaller than a proton. And we're then opening up this brand new window in the universe where we are actually probing directly the nature of space-time, the movement of space-time, and we'll also go back in cosmic history and look at some of the earliest gravitational imprints from the beginning of the universe. And it's a fairly stable configuration. We don't have to do much propulsion. We don't have to fly the spacecraft by hand. It's a dynamically very stable configuration. And the mission should last for 4 years, and it will absolutely revolutionize the work that we do. Euclid also looks at the dark universe, and again, this connects with galaxy formation and evolution and where the black holes are in the universe. Einstein predicted the universe is expanding, and it is, but in the 1990s, scientists looking at exploding supernova stars discovered that actually the universe is not only expanding, but that expansion is speeding up with time. So we have an accelerating universe, which is not predicted by Einstein. So there's clearly some physics beyond Einstein we have yet to discover. What Euclid will do is it will map the whole of the extragalactic sky back to 10 billion years in cosmic history, and will actually give us the most definitive measurement of dark energy, dark matter, and the coupling between them. We understand only 5% of the universe. Everything I've told you tonight is less than 5% of the whole universe, so we need to understand the other 95%. The reason Euclid is really special is because it's got beautiful optics, it does wide field, and it's very, very sensitive. When we first launched in 2023, we had a little bit of ice on the optics, and it really cut down the light. We have such good sensitivity that the thickness of that ice was thinner than a strand of DNA, and it was a problem for us. So we defrosted the optics 3 times, and now it's stable. And field of view is 2.5 times the size of the full moon. 1 shot gives us that, and we'll do 30,000 of those independent fields. It is an autonomous system, so the astronomers don't point it. It's got an autonomous algorithm. It knows how to map the sky to give the scientists the cover that they need. And that's the cover. The bit in the middle, of course, all of this has been done with Gaia, because this is our Milky Way, and this is the whole of the extragalactic universe that Euclid will do. And we've produced a few quick data releases so far, and it's, again, already transforming our view of the universe. These 3 deep fields were just to test that the scientists could do what they needed to do. And in fact, we already found 380,000 galaxies mapped using machine learning and artificial intelligence with 10,000 volunteers. We also found the distortion of space-time in the middle of galaxies. This is the picture that you get if you had a ground-based telescope. You know it's a fuzzy galaxy. Okay. But actually, if you look with Euclid, it's like putting spectacles on. That's the view you get from Euclid. And what this ring in the middle, this is called an Einstein ring. And it's actually because the light follows distorted space-time, and it gives you this very characteristic pattern. So when you see this pattern, and you know the galaxy and the background galaxy, scientists can actually work backwards and figure out what the distribution of mass is, so they can actually make maps of the hidden dark matter without being able to see it. And again, using artificial intelligence algorithms, instead of doing 1 galaxy at a time, we maybe know 4 of these. 500 lenses were discovered in the first quick look. So we're just finding these. We'll do 9 billion galaxies in 6 years, so it's going to transform all sorts of areas of astrophysics. So I do believe we're in a new area of discovery. Yes, we stand on the shoulders of giants. Everything from astroparticle physics, studying exotic particles like neutrinos and axion-like particles, through to the highest cosmic rays, the lowest energy, longest radio waves, going into space with all of the incredible missions that we're planning for the coming years, and particularly the transient universe, so mapping how things change at grand scales. So we were waking up in the beginning of our research group and over the last couple of decades, about 100 GRBs a year. With the Rubin Observatory, we'll probably have 1 million transients a night. I'm not waking up 1 million times. And the way we did it, we used to have a message on our phone, so the satellite would send a signal to the telescope and our phone would buzz and you wake up and go, whoa, 1 million buzzies a night? No, no, no. Anyway, it's very, very exciting, and we are going to go beyond Einstein because there's unknown physics that we're yet to discover. So this is what I'm proposing to our ministers, to our 23 member states, that we set the right level of resources so we can do our bit for discovery with the missions that we propose, that we need to start the technology development on now, and then we combine that with the other big technologies that are being built in international collaborations on the surface of the planet. And if we can put the lights down, I thought I would leave you with a tour of the cosmos with Euclid. I think we've come a long way in 15,000 years. Thank you very much.
Thank you so very much for this really exciting lecture. I think you showed really nicely how incredible the advancement in the angular resolution and all the other technology has been in the last 20 years or so, and how it all comes together from different perspectives, from ground-based observatories, space satellites, different wavelengths, gravitational waves, and so on. So is there any question from the audience? Please.
There should be another microphone.
Thank you. You said that at the center of our galaxy is a supermassive black hole.
Yeah.
What is the biggest that a black hole could be, and what is the smallest that a black hole could be?
What a hard question. The most massive black holes that we've found, they're very rare. They're about 10 to the 10, so that's 10 with 10 zeros after it, so 100 billion times the mass of our sun. They're often in galaxies in the early universe. They should not be that big that soon, and we don't know how to form and evolve them. So yeah, that's a good question. We also possibly think they might start to break the correlation between galaxy mass and black hole size, because when you measure the mass of the galaxy, the ball of stars, you can predict how massive the black hole should be in the center, and they might be kind of breaking that. So we're not quite sure how and why, but it tells us something important about how galaxies form and evolve. The smallest ones, as I say, if I squished you into a black hole, you'd be the smallest, but you'd evaporate and we wouldn't see you. But more seriously, the gamma ray bursts are really producing, those stellar mass black holes are about the mass of our sun, and they're a few kilometers across. So it gives you a scale. The supermassive black holes are about the size of the solar system. Thank you for the question.
Thank you. Any other question?
Thank you so much for this inspiring talk. I'm a PhD student here in the University of Gorica, and I want to ask you some personal question, if you don't mind.
I think you have to ask me about the magnetic fields first. I'm sorry.
No magnetic field involved. I want to ask you what motivated you to switch from the science, because now you were talking about all these scientific topics, to the administrative work. I mean, and how do you manage to combine all of that? Because I see that the articles are still published.
Yeah.
So how do you manage to do that? It's like you're a superwoman.
No, well, I have good teams. No, I mean, what I've formally done when I joined the European Space Agency, because I'm a custodian of all of that science portfolio, so I actually resigned all of my research collaborations. I resigned from, I was a full professor at the University of Bath, and I resigned from those research collaborations because I have to be unbiased, because it's a competitive process, and ultimately when we choose a mission, every scientific community needs to know that they have a fair and equitable chance in the competition. They should not have any worry or deep impression that I favoritize one science over another. Having been an academic and an active researcher all my life and supervised students and taught and worked in government, now I bring that together in this role. And the reason I described it as my dream job at the beginning is because what I get to do is I get to enable the science of the science community. So it's bigger than me, it's bigger than one person. I have to do it within tight budgets. There's a lot of public scrutiny because it's public taxpayers' money. And I get to join it from beginning to end. So I know the community well. I know what it's like to be a scientist and have your paper rejected or your proposal rejected. Referees, you didn't understand. So I understand that very much. And it's also allowed me to build more transparency with the scientific community, help them to understand how ESA works, and also to build stronger relationships with industry and start to bring the two together. When I visited Slovenia in March, as I said, Slovenia became a full member of ESA. It was wonderful to meet the minister, the state secretary, the space office, and help them to think about what's unique in Slovenia, what Slovenia's ambitions are, how to support a growing space industry, how to support and invest in the scientific ecosystem, and help that connection between the fundamental research and the technology development that happens in physics and engineering departments in top universities in Slovenia, and how to feed that into industry and do that all under a space umbrella. My PhD students, when I joined ESA, obviously I restructured their supervisory teams. That was work that we were already doing together. Their papers are coming out. So in tiny little moments I get in the night, I'll read their papers and send some comments, but ultimately they're leading those papers. So it's a huge honor to still be included in that collaboration, because that's work that I did before I joined ESA. And for me, when I get time to read a few papers and see where the frontier is, I don't have much time to do that, but this is a 4-year position in ESA. I gave up a permanent academic position to become an international civil servant. There's a potential for extension of this position, but that will be up to my Director General and the 23 countries. If they decide I've done a good job, they might ask me to stay for a little bit longer. But it's a huge privilege to enable all of these missions and to put a robust and trustworthy scientific method at the heart of all of that, as well as very transparent, good management of the finances, of the engineering, of the industrial contracts to ultimately deliver upon the science. And I hope you'll... What's your area of research?
Earth-rays.
Very good. Cherenkov telescope array, it's coming. Yeah? And also from space. Maybe you'll propose the next mission.
There are lots of good proposals for missions, and ESA unfortunately cannot fly them all, right? This is always a tough decision in the end to select the missions which will be adopted, and then they will fly. More questions maybe in the audience? Francesco?
Hi. talking about what you just said, and especially about proposals to ESA, etc., what are the main topics that ESA, like you showed before, for example, that we're looking for extraterrestrial life, etc., but what are the things that in proposals you look and you say, oh, this is great, I really want this, or you say, maybe this is...
So the process is very robust. So what we do when we are beginning to design the next, well, there are two things we do. Let me tell you about the overarching strategy. So every decade or so, we design a strategy. The one we're delivering at the moment is Cosmic Vision. The next one will be Voyage 2050. And the way we do that, we put a call for white papers out to the scientific community. It's sort of similar to NASA. And for Voyage 2050, we had over 100 science papers from the scientific community. So the ESA doesn't interfere in any of that. That's for the scientists. Then we had an expert panel of academics, so again, independent from ESA, who did the scientific review across all areas. So the expertise. Senior scientists who understand how it is to sit on a panel and not vote for their mission. They're looking for the best science. And there's no prejudgment on what that science topic should be. Those 100 white papers were then boiled down to our large flagship missions, so LISA, JUICE, and Athena are those big flagship missions, sort of 1.4 billion euro missions. They had 14 highly viable frontier proposals. Now, I don't have the money for 14. So they spent a year breaking all of those proposals up, and they came up with 3 main themes. And so we now have our theme for our next class mission, our L4 mission to Enceladus. So that's the icy moons of the distant planets and seeking life. And the whole of the planetary community are behind that and are preparing and helping us develop that mission. The next one really builds on the legacy of Gaia and Euclid, and it's from exoplanets to Milky Ways. And the last theme is fundamental physics of the universe. So in each of those, we will put an additional call for proposals out. Our medium class missions, we just put a call out this year for the 8th in the series, Euclid as medium class mission, maybe 500 million, 600 million euros. And we put that call for proposal out. So you have a budget, you have a mass limit, you have some constraints, and scientific consortia form, and they propose, and then we review those proposals with the science teams. So the first selection is on scientific excellence, frontier breakthrough science. We then will take, for M7, we had 30 proposals, and we selected 5 finalists based on frontier science. We then, our engineering teams then work with the scientific consortia, and the member states fund a little bit, to see if we can realize the technology. Because if it's a frontier mission, the technology mostly doesn't exist. Some will, you'll use existing technology and you'll evolve it. So there is then a period for those 5 competing teams to have some help to further develop their proposal. And it might be that you start to develop and maybe it becomes over cost and you think, okay, that's going to go out of the cost budget, so that falls out of the competition. But we may still find a way to incorporate that technology. One of the M7 missions of technology now will go on our L4 mission. So although that team will not lead that mission, they'll still get to do their science and they can support the next one. We then have 3 finalists, so we have 3 in the running at the moment. They get lots of project help from our engineers, from our project scientists to give them the best possible chance to be selected. And then again, we do a scientific, programmatic, technical, engineering, and financial review, and we pick one winner. And then that mission then goes into study phase for implementation, and then we bring it to our member states when the technologies are at a level of 5 out of 10, so mature enough to know that we can deliver. We then go to our 23 member states. I make the presentation on finance, engineering, science, and programmatic relevance, and does it fit in my cost budget, and how will I profile it over time? And the 23 countries then vote. A bit nerve-wracking, frankly. And the 23 members vote and say yes, go ahead, or no, okay? Now, if we've done our work well, they'll say yes, and we get to implement that mission, and that comes into the program. So you see it's quite complicated, but it's very transparent, and we've increased that transparency over the last couple of years because I got feedback from the science community. They didn't understand why their missions weren't selected. Everybody felt a little bit disgruntled. So we've helped that transparency, that people understand that process more. So we had a very strong response to our call for the 8th M-class mission and the 3rd fast-class mission. So Comet Interceptor is a fast-class mission, smaller mass, smaller budget, developed in quicker time, but still frontier world-leading science, because scientific excellence is the criterion of the program, and then we develop everything within budget. And some of the missions we also operate because they continue to deliver frontier science beyond the core time of the mission, and some of them have been there for 20, 25, in Hubble's case, 35 years. So again, we manage that long-term operation to maximize the science return. But that makes it a little bit clearer.
It's a complicated process, but in the end, the success rate for ESA is very high. If I'm not mistaken, there's no failed missions. Yeah, okay.
No, I mean, it's a different, I mean, we haven't got the, if you like, the money and it's public taxpayers. So one way to do things is try, fail and learn, right? But actually you need a different funding model for that. So I can't, sometimes people say, oh, you slow or you bureaucratic, but it's not. It's because we do all of the engineering modeling and then we make sure that that mission succeeds. Cluster was the 4 spacecraft that are now actually coming down after 20 years of studying the Earth-Sun interaction. And actually the very first realization of the cluster mission of those 4 spacecraft 25 years ago, they perished on the launch. So it was the maiden flight of Ariane 5 and it blew up on launch. And I remember watching on TV, I remember the silence and the crying. I mean, there were teams, instrument teams, scientists who spent 20 years building that. It was so shocking. Yeah. But the member states came together and said, we'll rebuild those satellites, and then it launched, and we've been studying the Earth-Sun interaction for 20 years.